For most years, the inner solar system is a quiet place. A handful of comets drift through, whispering past the planets before fading back into the dark. But in late 2025, the skies begin to behave differently restlessly. 7 major comets, all at once, are diving inward like a swarm of icy missiles. Among them is the interstellar behemoth, 3I, Atlas, a visitor from beyond the sun's domain, growing larger and brighter by the day. Across observatories on Earth and in orbit, astronomers scramble to map their trajectories. It's not just one comet we're studying, it's a cosmic traffic jam unlike anything seen since telescopes began recording the heavens. Within a tight 6-month window, 7 colossal objects are set to sweep past the sun and Earth, their glowing tails overlapping in time and space. Some experts whisper that the disturbance could even stir the sun itself, spiking solar storms as their electric trails carve through the solar wind. Others say one of these visitors might shine bright enough for everyone on Earth to see, with a naked eye reminder that the universe is still full of surprises. But a question haunts every late-night discussion in astronomy labs. Why now? Why, after decades of routine sky watching, are so many comets arriving together as if summoned by some unseen hand? The numbers alone are staggering. Most years, astronomers are lucky to get one or two bright comets close enough for detailed study. 3 in a year is remarkable, but 7, all diving toward the inner solar system within a few months, borders on impossible. Since the dawn of systematic sky surveys like Pan-STARRS, LINEAR, and the Atlas Project, no season has ever recorded this level of activity. The last time anything close occurred, telescopes still relied on fragile glass plates, a discovery spread by telegram. Yet this isn't a slow parade across years, it's a rush. Each object is arriving in quick succession, threading the same region of space like synchronized dancers. Some are long-period comets making rare returns from the frozen edge of the Oort cloud. Others are newcomers never seen before. And then there's 3I, Atlas, the anomaly from another star system. Its composition and orbit unlike anything native to our own. That one object alone would be a global headline in any other year. But alongside 6 others of significant size, the odds become astronomical. Statistically, since 2000, only 1 comet per year typically reaches naked eye brightness. Most years, the rest are faint ghosts detectable only through powerful telescopes. To see 7 major comets in a single season is more than rare, it's an outlier event, a celestial alignment that could take generations to repeat. For scientists at the Minor Planet Center, the pattern is mesmerizing and unsettling. Never before in the digital age has there been such a dense concentration of perihelion passes within the astronomical units of the sun. To make things stranger, the orbits of many of these comets share similar alignments to the ecliptic, the thin, flat plane where planets travel. It's as if an invisible gravitational hand guided them inward together. Comet discoveries have surged in recent decades thanks to robotic surveys and AI-driven sky scanners, but nearly all turn out to be faint, short-lived wisps. These 7 are different, bright, stable, close. Together they form something not seen before, a true swarm, a multi-act performance written across the heavens. Astronomers have begun treating it as one event rather than 7 separate occurrences. They track how each comet's orbit, tilt, and solar encounter might influence the others, whether their trails could cross, or their interactions could ripple through the solar wind. It's a cosmic choreography unlike anything in the modern record, and with every day that passes, the tension builds. The first to arrive is C. 2020 to enter Pan-STARRS, the quiet herald of the coming storm. It reaches perihelion on July 31st, far beyond Mars at a chilly 3.8 astronomical units from the sun. Too distant for the naked eye, it marks the opening act of calm before the solar winds start to roar. Next comes C. 2025 R to Swan, discovered on September 11th and racing to its closest approach to the sun just a day later. By October 21st, it sweeps past Earth at only 0.5 astronomical units, about 37 million kilometers, a close call by cosmic standards. Its movement is so rapid that its tail and coma evolve in real time, a living laboratory for scientists observing how sunlight, radiation, and magnetism sculpt a comet's form. For skywatchers in the northern hemisphere, Swan could blaze briefly in the pre-dawn sky, a ghostly torch between the stars. Hot on its heels is for P, stereo, diving toward the sun on September 27th with a perilously close perihelion of 0.52 astronomical units. Its orbit dips steeply below the ecliptic, disappearing into solar glare, out of reach for most Earth-based telescopes. But spacecraft observatories, especially the stereo mission for which it's named, prepare to capture rare footage from a unique angle, offering a new window into how comets behave near the solar furnace. Then come see 2025 K1 Atlas, the daredevil of the group. On October 8th, it will pass just 0.33 astronomical units from the sun, closer than Mercury ever ventures. Its icy nucleus will face brutal radiation and tides strong enough to tear lesser comets apart. For scientists, it's a perfect chance to witness volatile materials erupt and form new tails within hours. At nearly the same time, 3I, Atlas, the interstellar wanderer, slips behind the sun in superior conjunction. On October 21st, before rounding its own perihelion, on October 29th at 1.36, its path runs close to the planetary plane end. Alien traveler moving among familiar orbits. For a brief period, both 3I, Atlas, and Swan occupy prime positions for studying solar comet interactions. To Earthbound observers, though, they vanish hidden by the sun's brilliance, their drama unfolding behind a curtain of light by early November. See 2025 A6 Lemon takes the stage, reaching perihelion at 0.53 astronomical units, unlike the others. Its timing and angle make it visible after sunset, perhaps even bright enough to glimpse without a telescope. Predictions hint at a magnitude near 3.5, which would make it a true crowd favorite for casual stargazers. Finally, as the year closes, for OP, Ni drifts inward, faint and distant, reaching perihelion on December 19th at 2.1 astronomical units. It's not the brightest of the swarm, but its presence completes the story, a final reminder of how crowded the solar system has suddenly become. Each orbit, each perihelion, each crossing forms part of an intricate web. Together, they trace the dance between sunlight and gravity, a ballet of ice and fire millions of kilometers wide. When a comet nears the sun, its frozen heart awakens. Radiation vaporizes the ice, releasing clouds of dust and plasma that unfurl into distinct tails, one pale and sweeping, made of dust, the other thin and electric blue, made of charged ions. The latter tail is alive, constantly reshaped by the solar wind, a relentless storm of charged particles, flowing outward at hundreds of kilometers per second. Sometimes, these delicate structures are suddenly severed. Astronomers call it a tail disconnection event. A violent coronal mass ejection, or a twist in the sun's magnetic field, can slice through a comet's plasma sheath, cutting the old tail loose. For a few haunting hours, the comet drifts tailless through space before regrowing a new one, perfectly realigned to the sun's latest magnetic direction. These moments are more than visual wonders, they are direct signs of the sun's invisible moves, written across millions of kilometers of empty space. And in 2025, with 7 comets all threading the same stormy corridor, the heavens themselves are about to turn into a living map of solar fury. In April 2007, humanity caught one of the most unforgettable sights in modern astronomy. NASA's Stereo spacecraft watched, almost in disbelief, as a coronal mass ejection, a billion-ton blast of solar plasma, slammed into comet ink. Within minutes, the comet's glowing iron tail was sliced cleanly away, leaving a visible gap near its core. The old tail drifted off like smoke caught in the wind, while a new one began to regrow in perfect alignment with the shifting magnetic field. It was a moment that turned computer models into living proof, a textbook case of magnetic reconnection. Caught in real time, now, in late 2025, astronomers believe we're on the verge of seeing this drama unfold again, not once, but possibly several times, with 7 comets diving near the ecliptic just as the sun hits its solar maximum. The odds of witnessing live tail disconnection events have never been higher. Dust tails, wide and golden, usually ignore the sun's magnetic tantrums. They bend to gravity and sunlight, not magnetism. But the iron tails, those electric blue streamers made of charged gas, are different. They're fragile threads connected directly to the sun's invisible magnetic web. When a coronal mass ejection sweeps through, that connection can snap like a violin string. To anyone watching, the tail suddenly severs and floats away, a ghostly plume drifting across millions of kilometers of empty space. It's more than spectacle. It's a signature, a visible heartbeat of the sun's restless energy written across the dark. For solar physicists, the coming months feel like a countdown to revelation. And behind the excitement, a quiet unease. Inside NASA and ESA's solar research networks, a debate is growing louder. Could this sudden swarm of comets actually influence the sun itself? Some teams, especially at NASA's Community Coordinated Modeling Center (CCMC), believe so. Their simulations suggest that each comet, with its plume of plasma and dust, acts like a tiny magnetic disturbance. When several comets cross the heliospheric current sheet together, they could suddenly reshape the sun's magnetic field, even triggering localized instabilities. The models show dramatic possibilities, comets cutting through a CME's path, draping the sun's field lines around their bodies, until, snap, the tail disconnects in a burst of plasma only minutes later. And if 7 comets are active during solar maximum, the chances of multiple, cascading disconnections rise sharply. In some simulations, the extra plasma they shed even feeds turbulence in the solar wind, potentially priming the system for new eruptions, but others aren't convinced. Teams working with the Parker Solar Probe and ESA's Solar Orbiter point 2 years of field data. They argue that most tail disruptions are gentler, slow bends, faint kinks, or partial detachments that don't match the dramatic model predictions. The sun's own internal dynamics, they argue, are far more powerful than any comet's influence. According to their data, it's the natural reversals of the sun's global magnetic field, not passing comets, that drive most large-scale storms. Still, both sides agree on one thing: this season is a once-in-a-lifetime chance to find out. During solar maximum, CMEs can erupt to 5 times per week, each one a test case in motion. Space weather centers are preparing for non-stop observation. Citizen astronomers, equipped with backyard telescopes and online solar feeds, are ready to capture every twist and flare. A sudden disconnection could appear live on a webcam, witnessed simultaneously by scientists and stargazers around the world. And at the center of all this cosmic traffic is 3I, Atlas, the most mysterious traveler of them all. When astronomers first plotted its orbit, the math didn't fit anything known. Its path was hyperbolic, its speed to high, its eccentricity greater than 1. That meant only one thing: this comet isn't from here. It's not a visitor on a long loop. It's passing through, never to return. Only to other interstellar objects have ever been confirmed before it. The enigmatic Oumuamua in 2017 and comet Borisov in 2019. But Atlas is different. Early Hubble and James Webb data suggest a nucleus somewhere between 300 meters and 5.6 kilometers across, small by planetary standards, or wrapped in a coma nearly 700,000 kilometers wide, almost as large as Jupiter. And it's still expanding. Its chemistry is even stranger. Most comets are dominated by water vapor, but Atlas's coma glows with carbon dioxide and exotic volatiles, gases more at home. In alien star systems, cyanide appears only faintly, water barely at all. It's a chemical fingerprint from a different sun, a different origin story, a different world. Its motion adds to the mystery, entering our system at a steep 5-degree angle to the ecliptic, traveling at a velocity that leaves no doubt of its interstellar birth. Each new reading gives scientists something they've never had before: a direct comparison between our solar system's building blocks and those forged around another star. As Atlas nears its closest pass, it leaves behind a faint trail of dust and debris that Earth's orbit may cross in 2026, a gift to planetary defense researchers eager to study true interstellar material up close. For the first time, for now, 3I, Atlas is rewriting what we know about the solar system's boundaries and what lies beyond them. As the swarm intensifies, the sky itself becomes a theater. Before dawn on October 21st, Comet SWAN makes its closest approach to Earth at just 0.5 astronomical units, about 37 million kilometers. Through even modest binoculars, its tail stretches over 2.5 degrees across the sky, 5 times the apparent width of the full moon, faint but distinct. It's visible from dark skies across the northern hemisphere, climbing nearly 40 degrees above the horizon as the sun begins to rise. At the same moment, 3I, Atlas slips behind the sun, invisible to earthbound telescopes, but still tracked by space-based observatories like SOHO and Stereo on live solar feeds. It appears as a moving ember against the blinding corona, a visitor from another world brushing the edge of our star. Anyone, anywhere, can watch this unfold in real time, a front row seat to an interstellar crossing. Then, as October gives way to November, see, 2025 A6 Lemon takes center stage in the evening sky. Predictions suggest it could reach magnitude 3.5, bright enough to see without a telescope. From the northern hemisphere, it will hover low in the southwest after sunset, its tail brightening nightly as it swings around the sun on November 8th. For many, it may become the most visible comet in years, a rare spectacle to the naked eye. Astronomers mark the best observing nights, October 21st for Swan, and November 6th through 12th for Lemon's fiery display. For the rest, the action belongs to the coronagraphs, online instruments streaming the solar system's private show, where comets dance dangerously close to the sun's burning surface. But predicting comets is never simple. They are nature's wild cards. A small shift in spin, a hidden crack, a surge of heat, and everything can change overnight. Some flare into brilliance, outshining every forecast. Others crumble silently, their glow fading into nothing. Even with all the data from Hubble, JWST, and the Parker Solar Probe, brightness predictions can miss by the full magnitudes or more. For 3I, Atlas, the uncertainties run deeper than ever. Its size, its mass, its true composition, all are still blurred by distance and mystery. Its carbon dioxide-rich coma keeps growing, but no one knows if it hides water ice beneath, or something entirely new. Every new observation forces scientists to revise their models, reshaping theories in real time. What is certain is that this swarm, this fleeting alignment of 7 cosmic travelers, is giving us something we've never had before, a full-scale laboratory written across the heavens. Each comet acts as both witness and messenger, revealing how sunlight, magnetism, and gravity weave together to shape the solar system. And as the 2025 season unfolds, it's clear this isn't just a collection of icy visitors. It's a story about how alive our solar system really is, dynamic, unpredictable, and still full of cosmic surprises waiting just beyond the glow of dawn.